Okay, let us discuss this problem. So this is a quite good problem. So we have this question says we have 2 mole of an ideal monatomic gas. So what are the things that is given? So you have a 2 mole of ideal monatomic gas. So you have 2 mole of ideal. So ideal means I can apply P which equals to nRT. So monoatomic. So what is the meaning of monoatomic? You remember. So if I know this gas is monoatomic, so I have ideal. This means if I have ideal something, now this means I can apply P which equals to nRT. So that is a given to you. So the gas is ideal, so this means I can apply P which equals to nRT. Gas is monoatomic. So this means if I will need somewhere in the question, I can apply Cv is equals to 3 by 2R. Are you getting it out? So this is for monatomic. Now the question says this gas has been taken through a cycle A, B, C, A. So this gas initial situation is here, and this is taken to B, B first, then C and C to A. So this is a cyclic process. So this is a cyclic process, A to B, B to C, C to A. So this process is a cyclic process. If you remember, in cyclic process, state functions are 0 and internal energy is 0. So I can say change in internal energy through the cycle is 0. So change in internal energy through the cycle is 0. That is the case in this problem we have. Now the question also says during the process AB, the pressure and temperature, multiple of pressure and temperature remains constant. The equation of process AB is Pt equals to constant. So you see that is given to you. So equation for path AB or equation for process AB. So this is given to you, that is P into T is equals to constant. Are you getting or not? That is given to you. Basically we can calculate the value of this constant. You see, if I know at any point what is the, if I know any point on this line, I basically get the constant value. You see here P1 into T2 2T1. So 2P1 T1 is the constant. Here also you see 2P1 into T1, so that is 2P1 T1. So what is the value of constant? So I can have P1 into, if I plug the value 0.1, so P1 into 2T1, this is equals to constant. So now I know the equation of the constant value, that is P1 into, so I can plug this into equation. So P1 is equals to P1 Pt is equals to 2P1 T1. So this is the equation for process AB. Are you getting or not? So this is equation for process AB. Simple. Now the question says calculate the work done in the process AB. So we have to calculate what is the work done in the process AB. That is the easy task. So if you remember, so we have to calculate work done in process AB. This thing we have to calculate. If you remember, the work done is nothing but integral P dV. So work done is given by integral P dV. Do you remember? So this integral is given by P dV. Now I have to calculate this P dV. So you see in this process 1 you have P and T. So you know P1 T1, you know P2 T2, you can calculate. So let us say how can you calculate P dV? So you see you have one ideal gas equation, PV is equals to nRT. Now I need P dV. So I have to have, I can do something so that I can eliminate P, or other way around I can eliminate T because the process is given. So I have to utilize the process equation, that is Pt equals to constant. So why not we multiply both sides by P? So if we multiply this equation, ideal gas equation, both sides by T or P, so this is P into T, and P into T is constant, that is P square V, and this P into T is equals to constant, and the value of constant is 2P1 T1. That is given. So you see what we will have. So we will have P square V is equals to 2 P1 T1 and R. N is constant, number of mole is constant. This is for 2 mole of. So now I can write this is P square V. Same thing I am writing here. If I plug the value of number of mole, there are 2 mole of gases. So 2 into 2 4. So we will have 4 P1 T1, and this is R. R is also constant. Now what you need, you have to find what is the work done. So that is P dV. So let us differentiate this equation. Let us call this equation as equation number 1. If I differentiate, so I will have 2P dPV plus, and then I will leave P square differentiate V dV is equals to 0. So if you take P common, so this becomes 2V dP plus PdV is equals to 0. This means what? You have PdV, this is equals to minus 2V dP. So this is the value of PdV. Are you getting or not? So let us say try to find work done. So dW is nothing but integral PdV, and this is minus 2V dP. So I have to do some more calculation. So you see I have V, but here I have dP. So I have to change this B in terms of P. So you see what can I do? So I have this equation I have here. So that is, I can calculate from here what is V. So if I see this process, or you can think the same thing. So from equation 1, so this is the equation 1. So from equation 1 I can write this is, what is V? V is nothing but 4P1T1R by P square. So this is V. If I plug this value of V in this equation, so dW becomes minus 2, and this V is simply 4P1T1 by R, so into R, and this divided by P square dP. Now things are basically constant, so I can take outside. So this is 8 P1T1R, and this is simply dP by R square, dP by P square. So 1 by P square, integral of 1 by P square is minus 1 by P, so minus minus plus, so we will have 8 P1T1R, and this is minus 1 by P, so minus is basically cancelled here, so I will have simply 1 by P1, and I have to integrate what is the initial pressure. You see here, initial pressure is P1 and final pressure is 2P1, so I have to integrate from P1 to 2P1. So this is, this is P, not P1. So you see this is P simply, and you have to integrate from P1 to 2P1. So if you do this one, what you will have? You will have 8 P1T1R, and this is 1 by 2P1 minus 1 by P1. So you will have minus 1 by 2P1. So this is minus 8 P1T1R divided by 2P1. So P1 goes. So you will have 4 minus 4 and T1R. Are you getting or not? So this is the work done. Now you see the question says what is the value of R. So R is given to you. Basically you have to answer in terms of R. T1 is given to you. So 300 Kelvin. So 300 Kelvin. So this is 300 Kelvin. If you plug this value, so this becomes for 1200. So minus 1200 R. So this is the work done by the gas. You getting or not? So this is a work done by the gas, but the question asks work done on the gas. So on the gas, then I have to take a positive sign. This is work done by the gas. So this is important point. So this is work done. So let us say, so work done in process AB by the gas, this is equals to minus 1200 R. So work done on the gas, this will equals to plus 1200 R. Are you getting around? Now let us discuss part B and part C. So what is the part B? This says heat absorbed or released by the gas in each of the process. So I have to find what is the heat released in process AB. So if I know dW, and if I can calculate dU in process AB, so change in internal energy is nothing but NCV dt. If you remember, N is 2 and CV is 3 by 2R. This is a monoatomic gas, and it is what? So final temperature you see. So this says final temperature is T1, initial temperature is 2T1. So T1 minus 2T1. So you will have T1 minus 2T1 here. So this is T1 minus 2T1. So you will have 3R T1 with a minus sign. Are you getting? So what is this value? So 3R into 2, so for 300 into 300 minus 900 R. So what is dQ in process AB? So I can calculate dQ in process AB by simply writing dQ is equals to du plus dW, and dW we have already calculated. This is minus 120 R. This is work done on the gas and minus on by the gas. So we have to write in this equation, this is the work done by the gas. Are you getting or not? So you have see, if you have a positive sign, then it becomes by the gas, negative sign on the gas. So in this case, work done by the gas is minus 1200 R. And what is du? This is minus 900 R. So this is total minus 2100 R. So this is the dq in process AB. We can similarly calculate a dq in process BC. So let us calculate dq in process BC. So that is asked here. So you see, we have to calculate heat absorbed in each process. So what is the heat absorbed in process BC? You see, in the process BC is a isobaric heating. So this is a P is constant. So we can easily calculate what is the work done. So in case of isobaric heating, if you remember, so if we have pressure constant, so path BC is nothing but, so this is the isobaric process. So if you remember, isobaric process, pressure is constant. So work done is very easy to find. So integral P dV, that will give you work done, and P is constant, so I can always write nRT by V, or P is constant, I can take P outside and dV. So this is simply P V2 minus V1, because pressure is constant. So if I can calculate V2 and V1, I can basically get. So let us say at this point, what is V2 and what is V1? So at this point, this gas follows ideal gas equation. So here I have pressure is 2P1 and T1. So at point B, what is the, you can calculate what is the basically volume. So PV is equals to nRT if I apply. So let me write here itself. So I can write. So point B, so I can write P, what is the pressure here? This is the 2P1. What is the temperature? So T1. So P1, V1. I need to have V1. So this is, here I will have V1. So this is V1 is equals to N or what is temperature? So this is temperature T1. So what is the volume V1? So this volume V1 is nothing but 2 goes out. So this 2 goes out. So RT1 by P1. So this is RT1 by P1. So this is volume at B. So let us call this as a volume at B. Are you getting? Similarly, we can calculate volume at C. What will be the change? Only thing is, in place of T1, we will have 2T1. So this is the only change. So I can analogically I can write what is the volume at C. So this will be R. In place of T1, I have to write 2T1. So this becomes 2RT1 by P1. So what is the change in volume? So simply 2RT1 by P1 minus RT1 by P1. So this becomes RT1 by P1. So this is the change in volume, RT1 by P1. So this is, so P and change in volume is RT1 by P1. And what is the constant pressure value? You see, what is the constant pressure value for this equation? So you see, the constant pressure value is 2P1. So I have to plug this value here, constant pressure value, that is 2P1. So if I write this as a 2P1, so this becomes 2P1 into RT1, and this divided by P1, so P1 goes out, so we will have 2RT1, and T1 we have already know, this is 300, so this becomes 600 R. Are you getting or not? So you see, in this process dW is this. What is du? So du for BC process, and du is nothing but mCv dt. So Cv is 3 by 2 R. And what is dt? So you see, initial temperature is T1 and the final temperature is 2T1. So change is simply T1. So you see, in this case we will have change in temperature is simply T1. So we will have 3R T1, and T1 is 300. So 3 into 3 900. So you have 900 R. So what is dq in process BC? So simply dW plus du. dq is du plus dW. So 600 R plus 900 R. So this becomes 1500 R. Simple. Are you getting or not? So this is the heat change in process BC. Similarly, we can calculate heat change in process CA. So let us discuss this one. So what we have, so let us try to analyze what kind of process you have in CA. So this process, temperature is constant, isothermal process. Are you getting? So in isothermal process, what is the work done? If you remember in RT log Vm by Vi, so I can use directly. So this is a isothermal process. Isothermal process, temperature is constant. One more important point. So this is dW is, if you remember, this comes out to be nRT log ln Vf by Vi. We can prove this expression even if you don't remember. So this is P dV is work done, and P is nothing but nRT by V and dV if I apply ideal gas equation. So temperature is constant, I can take this outside, so dV by V is ln V, so this becomes nRT ln Vf by Vi, because I have to integrate from initial to final volume. So work done in process AC or CA is basically nRT. What is the final volume, what is the initial volume? So we have to see here. So you see, at this point we have already calculated what is the volume at point C. We can also calculate the volume at A. So let us write P is equals to nRT at 8. So P is P1, and let us say volume is VA. So N is 2, and R is R, and T is temperature at point A is basically 2T1. So I have to write 2T1. So what is the volume at A? So you have a volume at A is 4RT1 by P1. So this is 4RT1 by P1. So this is the volume at A. So VA. So you see, what is the volume at C? We have already calculated volume at C. This is 2RT1 by P1. So volume at A, that is the final volume. Volume at C, that is initial volume. So what is the ratio? Final by initial, that is final by initial. So ratio is 2. So Vf by Vi is 2. So now I know Vf by Vi, that is equals to 2. So if I plug this value here, so I will have nR, T is T1, okay, we will see this one, and Vf by V is ln 2. So now see, what is the temperature at this process? For this process, temperature is constant. What is the value of this constant? Constant is 2T1. So let us plug this constant value, that is 2T1. So if I write, this is N is number of mole is 2, R is gas constant is R, and T is basically 2T1 ln 2. So what is the total work done? So now I have total work done in process CA, that is a 4R. So this is T1, and T1 is 300 ln 2. So what we have? So we have 1200 R ln 2. So this is the work done in process CA. What is the change in internal energy for process CA? So if you see, this is 0. Why this is so? Because this is a isothermal process. So isothermal process temperature is constant. So T is constant, this means dt is 0, and I know du is given by NCV/dt formula. So dt is 0, so change in internal energy is 0. So it is easy to find dq for process CA, that is dW plus du, and du is 0 and dW is 1200 R ln 2. So this is simply 1200 R ln 2. So this is the work done. So this is the basically heat changes in process CA.